Something is wrong at the edge of the universe, not wrong in the way scientists expect when experiments fail or calculations drift. Wrong in the way that forces entire teams of physicists to go silent, stare at their screens, and question everything they thought they understood about the cosmos. A machine the size of a small car, running on less computing power than the phone in your pocket, launched almost 5 decades ago, is right now sending back data from a place no human instrument has ever reached before, and what it is reporting should not be possible. Not according to any model, not according to any theory, not according to anything we know. There are moments in the history of science when reality refuses to cooperate with the textbooks, when the data that comes in does not match the predictions that went out, when every equation, every model, every confident assumption made by the world's brightest minds gets quietly dismantled by a single stream of numbers arriving from the darkness. Well, this is one of those moments, and almost nobody is talking about it the way it deserves to be talked about. Let's start with what most people think they know about Voyager 2. They know it launched in 1977. They know it flew past Jupiter, Saturn, Uranus, and Neptune, the only spacecraft in human history to have visited all 4 outer planets. They know it's old, it's distant, and they assume that means it's essentially irrelevant in an era of Mars rovers and James Webb Space Telescopes. That assumption is wrong, profoundly, embarrassingly wrong. Because right now, as of 2025, Voyager 2 is doing something no other machine ever built by human hands has ever done before. And what it is finding out there is reshaping the most fundamental understanding scientists have of the space our solar system moves through. But here's where it gets strange. The closer scientists look at the data Voyager 2 is sending back, the more questions emerge that nobody can answer. And those unanswered questions are not minor. They are not gaps to be filled in with a few more observations. They go to the very heart of how we thought interstellar space worked, what we thought the boundary of our solar system looked like, and most disturbingly, what is actually out there in the dark between the stars. What most people are not seeing is that this is not an old mission winding down. This is a live, active scientific emergency unfolding at the very edge of everything. Think about what it actually means to be where Voyager 2 is right now. As of 2025, this spacecraft is more than 13 billion miles from Earth. 13 billion miles. To put that in perspective, the average distance from the Earth to the Sun is roughly 93 million miles. Voyager 2 is now more than 139 times farther from us than the Sun itself. The signal it sends back, traveling at the speed of light, takes more than 19 hours to reach our receivers here on Earth. When Voyager 2 sends a message, the mission team has to wait nearly an entire day just to hear it. And when they send a command back, another 19 hours pass before it arrives. This is not a spacecraft being managed in real time. This is a conversation happening across the most extreme distances the human mind can barely comprehend. And this is where everything changes. Because despite that incomprehensible distance, despite running on technology designed in the 1970s, despite operating on a power budget that diminishes by approximately 4 watts every single year, Voyager 2C crossed a boundary in November 2018 that permanently altered the history of space exploration. It crossed the heliopause. That word, heliopause, needs to sit with you for a moment because it describes something almost mythological in its significance. The heliopause is the boundary beyond which the sun's solar wind can no longer reach. It is the outermost edge of the heliosphere, the enormous bubble of charged particles and magnetic fields that our sun creates and that envelops every planet in our solar system, including Earth. Everything inside the heliosphere exists under the sun's direct influence. Everything outside it exists in true interstellar space, the space between stars. And in 2018, Voyager 2 crossed that line. It became only the second human-made object in history, after Voyager 1 in 2012, to actually enter interstellar space. But read that again carefully. We've known about that crossing since 2018. So why is 2025 the year scientists are increasingly unsettled? Why are new teams being assembled to study Voyager 2's transmissions with fresh urgency? The answer lies in what the spacecraft has been revealing, not just at the moment of crossing, but in every year since, and in what those revelations have quietly, systematically demolished about our existing understanding of the cosmos. When Voyager 2 crossed the heliopause, it had 5 science instruments still functioning: a magnetic field sensor, 2 instruments for detecting energetic particles across different energy ranges, and 2 instruments for studying plasma, the electrically charged gas that fills both the interior of our heliosphere and the interstellar medium beyond it. Scientists had spent decades building theoretical models predicting what those instruments would find. They had computer simulations. They had data from Voyager 1's earlier crossing. They thought they were prepared. They were not. The first major revelation was about the magnetic field. According to informed sources within the heliophysics community, The theoretical expectation was that as Voyager 2 crossed from the inside of the heliosphere to the outside, there would be a dramatic realignment of the magnetic field. The solar magnetic field and the interstellar magnetic field were assumed to point in different directions, because they are generated by completely different astrophysical processes operating across incomprehensible distances. What Voyager 2's magnetometer found was something that stopped researchers cold. The magnetic field just beyond the heliopause was almost perfectly parallel to the magnetic field inside it. They were aligned. They were pointing in essentially the same direction. This had already been seen by Voyager 1, but scientists had hoped it might be a coincidence, a quirk of where Voyager 1 happened to exit. Voyager 2 exited the heliosphere at a completely different location, at a different angle, at a different point in the solar cycle, and yet it found the same thing. The magnetic fields were aligned. That is not supposed to happen. There is no clean theoretical explanation for why the sun's magnetic field and the interstellar magnetic field would be parallel, and this is only the beginning. The plasma data was worse, or more accurately, it was more bewildering. Scientists had spent years developing models for the plasma environment in the interstellar medium, the density, the temperature, the flow. The instruments on board Voyager 2 measured the actual properties of this plasma for the first time in history. And the numbers were wrong, not slightly off, not within a reasonable margin of error. Wrong in a way that forced researchers to go back and reconsider. The interstellar magnetic field was found to be 2 to 3 times stronger than theoretical models had predicted. Think about what that means. Every model predicting how the heliosphere interacts with interstellar space, every simulation of how our solar system is protected from galactic cosmic rays, was built on an assumed magnetic field strength, and that assumption was off by a factor of 2 or 3. As a direct consequence of this stronger than expected magnetic field, the pressure that interstellar particles exert on our heliosphere, pushing against it, compressing it, shaping it, was found to be up to 10 times greater than previously believed. 10 times. The universe outside our solar bubble is pushing back against us far harder than we thought, and we had no idea. But here's where it gets worse. Because the shape of the heliosphere itself, the shape of the protective cocoon that shields every living thing on Earth from the full ferocity of galactic cosmic radiation, turns out to be something we don't actually understand. For decades, the dominant model depicted the heliosphere as something like a comet, a rounded leading edge in the direction of the sun's travel through the galaxy, and a long trailing tail streaming up behind it. Neat, predictable, comprehensible. But the data from the Voyager probes, combined with observations from other missions, has forced scientists to question whether this model is even close to accurate. Research published in early 2024 suggests the boundary region, the heliopause, is not a thin, sharp line the way scientists once believed. Instead, it appears to be a thick, layered, complex transition zone. The real story is that the edge of our solar system is not a wall. It's a blurred, dynamic, shifting frontier that we barely understand. And there's something else hidden in the data that should change how you think about your place in the universe. When Voyager 2's instruments detected the crossing of the heliopause, they found something at the boundary that defies easy explanation. There was a slight but measurable increase in plasma density just inside the heliosphere near the edge. The plasma appeared to be compressed against the inner lining of our solar bubble. Scientists confirmed this observation, but they cannot fully explain what is causing it. Something, the pressure of interstellar space, the interaction between the two magnetic fields, some as yet unknown physical mechanism, is squeezing the interior of the heliosphere from the outside. Think about that. There are forces acting on the boundary of our solar system that our best models did not predict and cannot currently explain. The heliosphere also appears to be leaking. This is perhaps one of the most quietly alarming discoveries to come out of the Voyager 2 data, and one that receives almost no mainstream attention. One of Voyager 2's particle instruments detected a measurable trickle of particles from inside the heliosphere slipping through the heliopause and escaping into interstellar space. The boundary is not sealed. It is not the perfect shield. Astronomers once assumed. Now, the scale of this leakage may be small. It may ultimately prove harmless in any practical sense, but the discovery reveals that the theoretical model of a clean, impermeable boundary between our solar environment and interstellar space is simply false. The hull, to use an analogy NASA itself has employed, is leaky, and we're only now beginning to understand what that means. Meanwhile, throughout the years since its heliopause crossing, Voyager 2's instruments continued to register data that kept challenging assumptions. In the summer of 2025, according to reports from observers of the mission, the spacecraft's remaining instruments began detecting unusual fluctuations in magnetic field readings and plasma density in the surrounding interstellar environment. The signals were unusual enough that NASA scientists began prioritizing all communication windows with the spacecraft to ensure continuous data reception. A new team of researchers began studying the transmissions more intensively, trying to understand what the spacecraft might be encountering in the interstellar medium. There are scientists who believe Voyager 2 may have passed through or near a previously unmapped interstellar plasma structure, a vast region of charged particles and magnetic fields whose properties differ from the surrounding interstellar medium. Some researchers have proposed the possibility of a gigantic interstellar plasma cloud, dense and dynamic, behaving in ways that current models cannot account for. And the data suggests this structure may not be static. This is not science fiction. This is what the instruments are reporting from 13 billion miles away. But there is another dimension to this story that makes it even more urgent, and it has to do with time. Voyager 2 is dying, not in a dramatic, explosive way. In the slow, inevitable, heartbreaking way of entropy, the spacecraft is powered by a radioisotope thermoelectric generator, a device that converts heat from the decay of plutonium-238 into electricity. This system does not require solar panels. It does not require a fuel supply in the conventional sense. It is elegant and reliable and entirely dependent on the rate at which plutonium decays. And that decay rate is fixed, immutable, inevitable. Both Voyager 1 and Voyager 2 lose approximately 4 watts of power every single year. Every year the voltage drops a little further. Every year the instruments operate on a slightly thinner margin. And every year, the mission team at NASA's Jet Propulsion Laboratory faces increasingly painful decisions about what to turn off. In October 2024, NASA shut down Voyager 2's plasma science instrument. That instrument had been instrumental, in the most literal sense of the word, in detecting and confirming the spacecraft's crossing of the heliopause. It had given scientists their first direct measurements of plasma conditions in interstellar space, and it was switched off because the power budget demanded it. Then, in March 2025, another instrument fell dark. Voyager 2's low-energy charged particle instrument, a sophisticated system of telescopes designed to measure ions, electrons, and cosmic rays from both our solar system and the galaxy, was officially decommissioned. NASA confirmed the shutdown command was sent and executed, with the signal taking approximately 23 hours to reach the spacecraft at the speed of light. Each of these instruments had been one of 11 that Voyager 2 launched with in 1977. 7 have now been turned off. 3 remain operational. And one of those 3, the cosmic ray subsystem, is scheduled for shutdown in 2026. The 2 instruments that will remain active for the foreseeable future are Voyager 2's magnetic field sensor and its plasma wave instrument. These 2 will continue to listen to the universe from beyond the edge of our solar system for as long as the power holds out. Engineers believe this spacecraft has enough remaining energy to operate at least 1 instrument into the 2030s, but that window is closing. And the scientific community knows it. There is a quiet desperation in the way researchers are now approaching the Voyager data, a sense that every year, every month, every data packet represents an opportunity that will never come again. No other human-made spacecraft currently exists in interstellar space. No other mission to date has been given the resources and timeline to reach that environment. The Voyager probes are alone out there, and they are nearly silent. What most people are not seeing is the broader implication of everything Voyager 2 has discovered. This is not a story about a single spacecraft finding a few interesting anomalies. This is a story about humanity's fundamental model of the cosmos being challenged in ways that will take decades to fully process. Consider the heliosphere itself. We live inside it. Every human being who has ever lived has spent their entire life inside this electromagnetic bubble. It is, in the most real sense of the word, our cosmic home, and we thought we understood it. We thought we had a reasonably accurate picture of its shape, its size, its boundary conditions, its relationship with the interstellar medium surrounding it. Voyager 2 has revealed that picture to be an approximation, a rough sketch that misses crucial details and gets key dimensions wrong. The magnetic field alignment at the heliopause still has no fully satisfying explanation. The unexpected pressure from interstellar space has forced updates to every model predicting how cosmic radiation reaches Earth. The apparent thickness and complexity of the boundary zone, the fact that the edge of our solar system is a layered dynamic transition rather than a sharp line, changes everything about how scientists think about the interface between our sun's domain and the interstellar medium. And the anomalous fluctuations being detected in Voyager 2's most recent data suggest that the interstellar medium itself, the region between the stars, is not the uniform featureless void that textbook diagrams have always implied. It has structure, it has variation, it has regions of higher and lower density, stronger and weaker magnetic fields, unexpected plasma formations that we are only now beginning to detect. And here is the deepest question, the one that haunts every physicist who works on this data. If the interstellar magnetic field is 2 to 3 times stronger than our models predicted, and if interstellar particles are pushing against our heliosphere with up to 10 times more force than expected, What does that tell us about the long-term stability of the heliosphere itself? The heliosphere is not permanent. It is not inviolable. It is a dynamic structure maintained by the constant outflow of solar wind, and the sun's output varies. Over geological timescales, scientists believe the heliosphere has expanded and contracted in response to changes in solar activity. There is evidence in the geological record, in ancient cosmic ray signatures preserved in rocks and ice cores, that the Earth has been exposed to dramatically elevated levels of galactic cosmic radiation in the distant past, consistent with periods when the heliosphere was weakened or reconfigured. If the external pressure on the heliosphere is 10 times greater than we believed, that changes every calculation about those historical events. It changes the baseline, and it raises questions about what the heliosphere's future behavior might look like. Meanwhile, there is another development unfolding in parallel that adds an entirely different dimension to this story. Because while Voyager 2 has been sending back its unprecedented data from interstellar space, scientists have simultaneously been revisiting an earlier chapter of its mission and finding new surprises there as well. In November 2024, a study published in Nature Astronomy revisited Voyager 2's 1986 flyby of Uranus, a flyby that happened 38 years ago. The flyby had puzzled scientists for decades because the data showed Uranus's magnetosphere in a highly unusual and seemingly contradictory state. The magnetic field was tilted at a wild angle relative to the planet's rotation axis. The magnetosphere appeared chaotic, asymmetric, and nothing like what theory predicted it should look like. For years, scientists simply concluded that Uranus was a genuinely bizarre planet and moved on. But the 2024 reanalysis revealed something different. Voyager 2 had arrived at Uranus during a period of extraordinary magnetic disturbance. Essentially, Uranus was in the middle of a magnetic storm, and the spacecraft had captured a snapshot of the planet at its most anomalous moment. As the lead project scientist put it, the flyby was packed with surprises, and for decades, scientists searched for an explanation. The new work shows that what Voyager 2 captured was not a representative picture of Uranus's normal state. It was a single frame from a particularly chaotic moment, and that means everything scientists concluded about Uranus based on Voyager 2's data needs to be revisited, revised, and in many cases, fundamentally rethought. Think about what that means for the larger picture. An entire planet's classification, its placement within our understanding of the solar system's structure, the theories built around its atmospheric and magnetic properties, all of it was shaped by data collected in a matter of hours during a single flyby nearly 4 decades ago. Data that was captured, it now turns out, at precisely the wrong moment. Science is built on this kind of vulnerability. A single observation made at a single point in time becomes the foundation for an entire edifice of theory. And then one day, something forces a re-examination, and the edifice shakes. This is what Voyager 2 keeps doing. Decade after decade, it keeps generating moments of re-examination. First, it was Jupiter, where the spacecraft discovered active volcanoes on Io, the first active volcanic activity ever observed on any body other than Earth. Then Saturn, where the true complexity of the ring system was revealed in breathtaking detail. Then Uranus, whose strange magnetic character launched decades of scientific debate. Then Neptune, where winds of nearly 1,200 miles per hour were detected on a world so distant it receives less than 1% of the sunlight that reaches Earth. Then the heliopause. Then the interstellar medium. And now, in the final years of its operational life, with its instruments being switched off one by one to conserve the last dregs of its nuclear power supply, it is still generating data that forces scientists to stop, reconsider, and wonder. The real story is that Voyager 2 was never just a spacecraft. It was a probe into the unknown, in the most literal, non-metaphorical sense of that phrase. It was sent into territory nobody had ever mapped, to measure things nobody had ever measured in conditions nobody could fully predict. And everything it has found has been more complicated, more surprising, and more deeply puzzling than the people who built it ever anticipated. The universe, it turns out, does not simplify as you move farther from home. It complexifies, it adds layers, it reveals structures that were invisible from within. There is something philosophically profound happening here that goes beyond the science. Voyager 2 was built by human beings who are no longer alive. It carries a golden record, a physical message encoded with sounds and images of life on Earth, intended not for any scientific purpose, but for the possibility, however remote, that something or someone else out there might one day find it. The people who made that decision understood that they were building something that would outlast them, that the mission would continue long after the builders themselves had returned to dust. And they were right. The engineers who designed Voyager 2's instruments in the 1970s could not have predicted that their creation would still be transmitting data across 13 billion miles of space in 2025. They could not have predicted that it would be revealing mysteries about the structure of the heliosphere that the entire subsequent generation of theoretical astrophysicists would struggle to explain. And the mission team at JPL, the men and women who have dedicated their careers to listening for Voyager 2's faint signal across the void, are now making decisions that feel more like hospice care than mission operations. Which instrument turn off next? How to squeeze another year, another month, another week of data from a system that was designed to last 5 years and has now been running for 48. There is a scientist who was quoted in relation to this mission saying that when it ends, they plan to retire alongside it because Voyager has been their entire career. That is not the language of engineering. That is the language of grief. It tells you everything about what this mission means to the people closest to it. According to informed sources tracking the mission's future timeline, Voyager 2's cosmic ray subsystem is scheduled to go dark in 2026. After that, only 2 instruments will remain, the magnetometer and the plasma wave instrument. Engineers project that at least 1 instrument may remain operational into the 2030s, but each year brings new power losses, new decisions, new silences. The signal from interstellar space grows fainter not because the spacecraft is failing. It continues to function with extraordinary reliability, but because the energy that powers it is slowly, irreversibly running out. And here is what makes this feel like something more than a chapter of science history. Right now, there is no follow-up mission in place. The United States science community, in its most recent decadal survey for heliophysics, released in 2024, did not recommend an interstellar probe mission as a priority. The Voyager probes will eventually fall silent, and when they do, humanity will have no ears beyond the heliopause. No instruments in interstellar space, no direct measurements of the environment our solar system moves through. China is reportedly pursuing its own interstellar mission concept, which would potentially give that nation's scientists a platform that no American mission currently has on the drawing board. The gap between the end of Voyager and the beginning of any successor mission could be measured in decades. Think about that silence. Think about what it means to have a window into the interstellar medium, a window that has already shattered so many of our assumptions about the universe, and to watch that window slowly close, with no plan in place to open another one. Every piece of data from Voyager 2 is now being received with an awareness of finitude, of irreplaceability, of an opportunity that, once lost, cannot easily be recovered. Scientists are not just analyzing the data, they are trying to extract everything possible from it before the source goes quiet. What is waiting out there beyond the heliopause? The honest answer is that we don't know. We know far less than we thought we did before Voyager 2 crossed that boundary. The interstellar magnetic field is stronger than expected. The pressure on our heliosphere is greater than modeled. The boundary itself is thicker and more complex than theory predicted. The interstellar medium appears to have structure, regions of density and variation that our current instruments can barely characterize. In the summer of 2025, unusual fluctuations in magnetic field and plasma readings suggest Voyager 2 may have encountered something in the interstellar medium that does not fit existing categories. A pressure front, a plasma cloud, a galactic weather system moving through the space between stars. Scientists are still analyzing the data. And what if the interstellar medium is not merely a passive environment that our heliosphere moves through, but an active one? What if the structures within it, the pressure fronts, the plasma clouds, the variations in density and field strength, interact with the heliosphere in ways that affect the conditions inside it? What if the environment beyond our solar system is not simply background scenery, but a dynamic participant in the conditions that make life on Earth possible? These are not fringe questions. They are questions being asked by serious scientists analyzing real data from a real spacecraft. And they are questions for which, right now, there are no firm answers. Voyager 2 will eventually stop transmitting. The plutonium will decay below the threshold needed to power even a single instrument. The signal will stop. The golden record, physical and silent, will continue traveling through the interstellar medium for billions of years, passing through the Milky Way, through space that no telescope has ever directly observed, through darkness we cannot imagine. But the data it has already sent back, the measurements that contradicted our models, the discoveries that forced re-examination, the anomalies that have yet to be explained, that data will remain. Scientists will spend the next generation working through its implications. We sent a machine into the darkness, and the darkness answered back with questions we didn't know to ask. The magnetic fields aligned when they shouldn't. The pressure was 10 times greater than predicted. The boundary was thick when we thought it was thin. The heliosphere leaks. The interstellar medium has structure, and right now, somewhere 13 billion miles from home, an aging spacecraft built by people who are gone, running on fumes of nuclear decay, is still listening. What is it hearing? What have we not yet understood? And when it finally goes silent, what will that silence mean? The universe does not give up its secrets easily. And everything Voyager 2 has found so far suggests that the deepest secrets are the ones we haven't thought to look for yet. The ones waiting in the dark, just beyond the edge of everything we know.